Okay, good morning, everybody. Good morning. I want to finish those notes off that I didn't complete yesterday, and then I'll start the new session. But I'm not sure if any of it, or how many of you had a rocket course. But if you remember, I was going through a couple metrics yesterday. And one of them I said was a very important parameter was the specific impulse. And I said, one of these things you should remember in the back of your mind. If you remember, you're not going to remember everything. So what are the little tidbits that are important to remember? Well, the specific impulse is proportional to the square root of the flame temperature over the molecular weight. Now, that's an interesting result, and you can show it mathematically in the appendix notes that I have. But there is also something called, for gun propellants, the impetus, which is also a measure of how efficiently you use the propellant to produce work on the projectile. And you also find that's proportional to the square root of the flame temperature over the molecular weight. Now, for those who've studied detonations, you also find that the detonation speed is proportional to the square root of the flame temperature over the molecular weight of what's behind the wave. So again, that's a very useful thing to remember. The other thing I was talking about yesterday was the importance of the pressure exponent, particularly in explosives versus propellants. And this is a simple result that's in the appendix, and if anybody's taken a rocket course, you would find. And it's just a simple mass balance. So if I'm looking at, say, a rocket motor like that, and I have a grain in here, and I treat this region here as my control volume, okay? And as this propellant burns downward, there's a mass rate of gas going into the control volume, and then there's a mass rate going through the nozzle at the throat. And at steady state conditions, the nozzle is always choked, okay? And so what I can look at then, as a function of pressure here, I can look at the mass generation rate, which is going into the propellant, into the control volume, versus the mass discharge rate through the nozzle, okay? And the mass generation rate is just going to be proportional to the propellant surface area times the burning rate, okay, which is AP to the N, if you remember, okay, according to VA's law. If I look at the mass discharge rate and I assume my nozzle's choked, I can sort of represent that choking factor in a discharge coefficient and keep the equation simple. And I find under those conditions, the discharge rate's proportional linearly with respect to the pressure, and the mass discharge rate has this P to the N factor. So if I plot those curves as a function of pressure, I find the discharge rate goes like this. And depending on what I choose for my value of N, if it's greater than or less than 1, I get two different curves. So for example, if it's less than 1, I get this curve for the rate at which I'm putting mass into my control volume. Okay, and what you find then is this point right here is a stable point. And suppose all of a sudden now I developed a crack or something and there was a pressure perturbation in my motor, so all of a sudden I'm pushing more gas into the control volume. Okay, what that would mean then is the pressure wants to go upward. Okay, and if the pressure goes upward, what I find is always the discharge rate will exceed the generation rate into the system. And as a consequence of that, I'll be driven back to the stable point. And the same thing happens if I go to a lower pressure, I'll be driven back to the stable point. However, if N is greater than 1, then I get a curve that looks like this. Okay, and there you can see now if I had this positive pressure perturbation in my motor, this is going to be the rate at which I'm putting gas into my control volume, and then it's going to exceed my discharge rate. And so the pressure will just continually exponentially grow, and I'll have a catastrophe. Okay, so that's the importance of knowing what the value of N is. If I have an explosive, obviously I want N around 1 or larger. Okay, so let me go back to the notes and finish the notes off that we had yesterday. I guess that was here. Okay, we had been talking about different ways of measuring propellant regression rates. And we went through the strand. I was showing you at the end here, basically using a subscale motor. And I started to show you some results of burning rates. In this particular case, noting the slope break that was in the pressure exponent of JA2, a double base propellant, showing you the same sort of interesting effect around 20 megapascals for RDX and HMX. I showed you the self-deflagration rates for different monopropellants. And then I showed you what AP looks like as a function of burning rate, gave some simple observations of what was happening at the surface. And then I went on and showed you nitromethane. Again, around 18 megapascals, there's a significant slope break before it reestablishes a lower slope break or exponent. And I think I ended with this plot here, showing you that, you know, if I'm a formulator, I may be trying to establish a burn rate profile that looks like one of these curves. And it's really an empirical art. You know, we don't have models right now that are going to go out and say, well, if I come up with this new formulation, I can predict how this pressure-dependent curve is going to look like. So, as I said, I'm a formulator. I've done it for so many years. I've got this empirical knowledge, and I kind of just know what to do. And I check to see whether or not it works. So here's an example of a burning rate of a real aluminized AP-based solid composite. You can see in this particular case, I have a slope down here, acceleration, I have a plateau here, and I have another acceleration. And so you can look, you know, the formulator went through a number of iterations on coming up with how to establish that profile. I want to show you some other cases of how these burning rate profiles can change as a function of pressure. This is I mentioned this the other day, hydroxyammonium nitrate is a crystalline oxidizer that's dissolvable in water. And you also dissolve a fuel with that mixture, and you create what's referred to as a three-component, really monopropellant. And it's suggested as a replacement for hydrazine. But look at how it burns as a function of pressure. The way these experiments were done were the same way I showed you the nitromethane. You put this liquid substance in a quartz tube, you ignite it at the top here, and you visually watch the surface propagate downward. Okay, and then with the high-speed camera, I take that film, I know the framing rate, I can back out a burning rate. So on the right here is a case in which I was looking at the fuel that was added to this mixture was methanol, and you can see as a function of pressure, there's an immediate slope break, there's a plateau burning, it decreases, it comes back up, and I'll show you results at higher pressures. It'll eventually come back down and go back up again. So it's got a very complicated burn rate profile at function of pressure. And you can see on the left-hand side here, this is without the fuel, but if I just change the amount of water in the mixture, I can change basically the burning rate profile. And I'll talk a little bit more about these characteristics lately. Right now, I just want to show you, you know, AP to the N is not always a simple expression for examining how burn rates occur. Another thing that the formulator does is he'll add catalysts, okay? And he adds these catalysts to basically increase the burning rate, but also to control the burn rate profile as a function of pressure. Typically, if I have a catalytic reaction with a gas species, I end up lowering the activation energy of that process compared to a thermal reaction. Okay, and if I lower the activation energy, that means it's going to go faster at lower temperatures. And I see that same sort of consequence here happening at lower pressures where the burning process is slower and the low temperature chemistry becomes more important. So in fact, looking at the schematic at the top, again, plotting just the log of a burning rate versus the log of the pressure. If I have a propellant that has basically a linear profile on this log-log plot that's non-catalyzed, I could potentially add a catalyst to get what's referred to as a super rate at lower pressures. And then as I get to higher pressures, the thermal reaction with a higher activation energy starts to overcome the catalytic reaction with the lower activation energy, and I start to get a plateau before it increases again. Okay, and again, you can get a mesa burning, you can get just plateau burning. The particle size has a significant effect, and where those particles are located, even where the catalyst particles are located. The catalyst is going to act, if it's a composite propellant, is going to act most frequently on the AP oxidizer. So if I embed, say, nanoparticles of this metal oxide catalyst inside the AP particle, I've got the catalyst particles right where I want them versus somewhere else out in the matrix, and that'll affect also how the system burns. And I show at the bottom here just some different examples of, again, burn rate profiles as a function of pressures with and without catalysts, the fact that you can manipulate them. Okay, I think the last thing I wanted to say in this set of slides was the fact that I've been talking about steady state burning, but there's different modes of transient burning processes that's important, obviously, to energetic materials. The ignition process is a transient process. Flame spreading over the surface is a transient process, right? I was talking about burning strands, and I inhibit the side, but what I want to do is I want to make sure that when I ignite it, the top surface is uniformly lit right away so that it's a one-dimensional process. If I got a motor with a center perf, right, that has again, a shape like this, and I have this center perforation, and I ignite it back here, as I mentioned yesterday, what I'm going to want to do is make sure I spread the flame down the length of the internal hole before I start the regression rate radially, so that I know I've got a one-dimensional process. I can also have what's referred to as transient or dynamic burning, which addresses the problem that the instantaneous burning rate of a solid propellant under rapid pressure change is different from those under corresponding steady state pressures, and I'll give you an example of that in a second. Extinction is a transient process and establishes both the static and dynamic extinction boundaries. Combustion instability within a motor itself. What causes the fact that I'm coupling the heat release with the resonant frequencies in the chamber, and how do they couple? That's a transient process. So I wanted to say a few words about dynamic burning because it is a little bit unusual relative to solids and condensed phase materials versus gaseous systems. The dynamic or transient burning process often occurs under a rapid pressure excursion. It's caused by the finite relaxation times required for solid and or gas phases to adjust their temperature profiles. So remember, we have this thermal profile in the solid, and I'm also going to have basically a temperature gradient in the gas. And how quick those gradients readjust themselves is important. So it's caused by the finite relaxation times required for the solid or the gas phases to adjust their temperature profiles. The instantaneous burning rate under transient conditions can differ significantly from the steady state burning rate corresponding to the instantaneous pressure. The temperature profile or the thermal wave thickness is a function of pressure. The thermal wave thickness and hence the thermal energy content in the heat region of the solid propellant decreases when the pressure is increased. And now the main reason for dynamic burning is that during the rapid pressure excursion, the relatively thicker wave that existed at lower pressures does not have time to adjust to the thinner thermal wave at higher pressures. Thus, the propellant contains more thermal energy in the heated region than required for steady state burning, and a new higher pressure gives a higher burning rate than one would expect under steady state conditions. So you can see sort of what I'm talking about in this cartoon here. on the left here, I'm operating at, say, pressure P1, and this is, say, a lower pressure, and I have a thermal wave profile in the condensed phase that looks like this. Okay, then all of a sudden, above the surface here, the pressure jumps to P2, which is a higher pressure. Okay, and if I was running this as a steady state burning process at that new pressure, I'd have a thermal wave that looked like this. Okay, so the energy stored in this portion of the wave is much different than the energy stored in that portion of the wave. And so I'm looking at different characteristic times because of this pressure excursion. How quick can this thermal wave in the condensed phase readjust to its new thermal wave and distribute that energy that was an excess of energy that would normally be there at the higher pressure? And as a consequence of this, I can see what looks like the burning rate profile here on the right as a function of time. If I was operating under steady state conditions and I went from P1 to P2, I'd get something like this. But since of this extra stored energy in the solid, I actually get this overshoot and this dynamic burning then in that transition of going from the lower pressure to the higher pressure. And you can look at that by just looking at characteristic times. Okay, and what I'm going to be looking at then is the characteristic time for the non-reacting condensed phase with a regression rate of R sub B. So here, just based on thermal diffusivity, the characteristic time for diffusing that energy is the thermal diffusivity in the condensed phase over the burning rate squared. I can also do that and establish a characteristic time for the gaseous flame, which again is based on the thermal diffusivity in the gas phase versus the condensed phase, now over the gas velocity squared to get a characteristic time. And I can get a characteristic time for the surface reaction based on the activation energy of that process. And I can compare these three times here then to basically a characteristic time for pressure disturbance, okay, which is going to scale basically with 1 over the frequency of that pressure disturbance above the surface. Okay, and what you'll find then, you'll end up having basically steady state burning if the characteristic times for the condensed phase readjustment, the surface readjustment of the chemistry, and the readjustment of the gas phase flame itself is much smaller than the characteristic time for the pressure disturbance. However, if they're of the same order, then I'll have dynamic burning. Okay. Okay, another concept is recognize I have a pressure deflagration limit. All that's saying is if I go below a certain pressure, the propellant doesn't burn. Okay, so the chemistry itself needs to have a high enough density to have the collisions fast enough to basically produce a reaction. So for AP crystals or pressed AP crystals, this is near 20 bar. So if I just take a pellet of AP and try to burn it here in the atmosphere, it's not going to burn. If it was an inert, it's not going to burn. Okay, it won't self-deflagrate. But if I raise the pressure up to 20 bar and light it, it's going to propagate. And you can see the same sort of thing with composite propellants that have a binder in it too. So one typically defines a low pressure deflagration limit. Another thing to look at in terms of characterizing propellants, is it a smoky propellant energetic material, a reduced smoke, or a minimum smoke propellant? Smoky propellants typically have metals in them. The metals form a metal oxide, which because the metal oxide's a refractory material, it goes and forms a liquid or solid at very high temperatures. Okay, and when I basically have those particles go through the nozzle, I'm going to have basically a whole set of these particles out in the plume. A reduced smoke propellant is one without metal particles, but produces particles during the expansion process in the nozzle. So in the expansion process, the temperature and the pressure are lowering, and as a consequence of that, I'm going to eventually, particularly if I'm in space, and my pressure goes all the way to basically a vacuum, what I'm going to see is the water that was in the combustion products could start condensing out. And so I'm going to start forming water droplets, and the HCl will do the same thing. In fact, they'll combine to form hydrochloric acid. Okay, so again, I'll get a droplet that's going to look like a plume because of the condensation of those species. And then the last case here is the minimum smoke propellants are typically modified composite modified double base propellants because they do form very few condensed phase species. So I end this section just with a little bit of review. I mean, particularly if people want to look at some science issues, and I'll come back and address these later. Things we'd like to know more about, what determines that value of N? Is it a chemical effect? Is it a physical effect? And can we know it well enough to basically put it in models so that we can predict it eventually? Reaction channels affected by catalysts. Catalytic combustion and propellants is an area that hasn't been studied significantly. The reaction channels triggered by combustion instability. The contributing factors to plateau burning. And this often is seen more often with ionic compounds. Ammonium perchlorate is an ionic compound. The decomposition kinetics in the condensed phase. As a combustion community, we're now very good predicting kinetics in gas phase. We've developed the tools that if we have the time, we can actually develop good gas phase models. And that's also true for the systems that I've been talking about, the molecular structures that I've been showing you here. What we don't have a good understanding yet and the ability to build models for is in the condensed phase. So in a solid state reaction or in a liquid phase reaction, how do I fundamentally determine those? I mean, the experiments are very difficult. I mean, to do anything, measurement something, kinetically in real time in the condensed phase. So as a consequence of that, we rely more on modeling techniques. And that involves then quantum chemistry, molecular dynamics, and those sort of techniques that really start delving into the processes. One thing I'm going to show you eventually, how important are real gas effects. In gun propellants, we certainly get to very high pressures. We're also at high temperatures, but there's a transition regime where we may be transcritical going to supercritical, and then real gas effects are going to become important. Very rarely included in any sort of model or equilibrium calculation. You go off and do a ChemKin calculation. They have a real gas model now within it, but very rarely do you see people including that sort of analysis. And the data itself at those pressures, it has some uncertainty. And then the idea of looking at condensed phases formed in the gas phase. An area in hydrocarbon combustion that's been studied a lot is soot formation. Okay, well, we sort of have a very similar process in terms of that metal oxide formation that's being formed from metal combustion. So for example, if I'm burning aluminum, a lot of the aluminum may end up in the vapor phase, and it reacts with oxygen or other species to start forming aluminum oxides that eventually grow till they're large enough that they start to form a nucleation site, and they form a very small particle. And then you can go through the same sort of processes that occur in growth of soot, but for a metal oxide, and that's really not been studied at all. Okay, so I want to finish these notes, and I want to move on to the new set now. And that's really looking a little bit now more at some of the composite. I want to go back and again say a little bit about kinetics, I think, in this section. Okay, again, a little bit of review. We've talked about what are molecular and homogeneous energetic materials. They're premixed systems of energetic materials that are kinetically limited, not diffusion, because I've got the oxygen and the fuel molecularly bound. A monomolecular system is a single molecular system, which are typically pure materials. And I can assume often that a plastic bonded explosive is, because there's so little binder in it. I mentioned to you that some of the PBX formulations have like over 95% of the oxidizer and very little binder. So to a sort of a back-of-the-hand type analysis, it can be thought of as a monomolecular species. And molecularly mixed materials would be basically things like your double-based and triple-base. So again, I want to go a little bit through a nomenclature, a little bit of a repetition, but I think, getting familiar with these compounds is sometimes one of the first things you got to do to talk the language in energetics. And they can be classified just like one classifies hydrocarbons. So here I list aliphatics. So aliphatic organic compounds belong to basically the alkane, and alkyne classes of compounds, both open, chained, and cycloaliphatic groups. And then the major sources of oxidizers are from the nitro, which is an NO2 group, a nitrite, which is an ONO group, and then a nitrate, which is an ONO2 group, and a nitramine, which adds basically an NH group to it. Okay, so if you just look at I'm not going to go through all these in detail, but if you look at the left-hand column, I look at nitromethane, methyl nitrite, methyl nitrate. So all I'm doing is I'm taking off of methane, one of the hydrogen atoms, and I'm replacing it with an NO2 group to get nitromethane. In the case of the methyl nitrite, I still have the NO2 group, but I'm attaching one of the oxygens now to the carbon of the methyl group. Okay, and the methyl nitrate then is an NO3 group, so I have an oxygen attached to the carbon. Okay, and I can name, then I can have nitropropane, propyl nitrite, propyl nitrate, and I can do it right down the alkane chain and form different energetic materials like that. And then you can see, I'm not going to go through it, but on the right you can see other sort of aliphatic type chains I can have. And as I said, I can have cycloaliphatics. Sometimes these are also referred to as the nitramines. We've talked about these, very commonly used in propellants and explosives. As I note here, they're really not flat. In fact, they have different configurations which give different crystal structures, which are basically different solid phases. And so if I heat up HMX, as I heat it up in the solid phase, its crystalline structure will change, okay, before it starts to burn. And there's a small energy term that one has to account for if one's developing models for that. So you can see the difference between RDX and HMX. And the naming cyclotrimethylene trinitramine for RDX. And again, it's just a ring structure with the ring consisting of CN atoms, and off of the nitrogen, NO2 groups, and off of the carbon, 2 hydrogens. And going to HMX, I just increased the size. But it's a ring structure that is not a benzene ring, so it's just a cyclic aliphatic. And then I can have the aromatics. So all of these are based on the aromatic ring, where I have the resonance frequency stabilizing it. So starting with trinitrobenzene, you can see I have the benzene ring, and the trinitro just means I've added 3 nitro groups to it, okay, in place of the hydrogen. Right next to it, I have basically toluene, which is already taken off one of the H atoms and put a methyl group. And now I have basically trinitrotoluene, where I take off the additional 3 H atoms and put 3 nitro groups. Okay, and you can go around. The TATB is triamino, trinitrobenzene. So the triamino is putting the NH2 groups and then the NO2 groups. I can also now classify inorganics. The inorganic compounds do not have hydrocarbon backbones forming the bases of the molecules. These are often usually ionic acids and bases or salts. And so so here, 3 structures, ammonium nitrate, and you can see on the left there's basically a positively charged NH4, and on the right you have your NO3 that's negatively charged. When this starts to typically react, what happens is I have a proton transfer. So the H atom leaves the NH4 to form NH3 ammonia, and then I form basically move the H atom over and have HNO3. And you can see right below it, then I have ammonium perchlorate, very similar. I have basically an NH4 positively charged and a perchlorate that's negatively charged. This shows some of the newer materials. It's very hard to develop new materials that particularly go into use because they have to go through a lot of safety testing, and the regulations, at least in the US, are very difficult to actually get a new ingredient all the way to something that might go into practice. And so I show a few of the newer ones here. Ammonium dinitramide, ADN, ionic compound. This is an interesting compound because it was actually researched and discovered out at Stanford Research Institute, SRI, in California. And it was thought to be a big discovery here in the US. And since the US finally discovered it, the Russians came out and said, hey, we've been using that for the last 20 years. So you can see the type of interactions go on. The next one is the hydroxyammonium nitrate, HAN. This is the one that the US is looking at in terms of replacing hydrazine. The two on the right are very highly energetic, and the most recent is the one at the top, the acronym CL20, and you can see it's a pentagonal shape with a lot of NO2 groups on it, and right below it you can see octanitrocubane, which again is this cubic structure with a lot of NO2 groups on it. They're relatively sensitive but very fast burning and release a lot of energy. And the last compound I'll introduce you to that's relatively new, that's a lot of research has been done out at Los Alamos, is high nitrogen energetic compounds. And they fall into a class of the families I showed here: tetrazoles, azides, tetrazines, furazans. And what you can see is they have different types of ring structures or linear, but they're highly loaded with the nitrogen atom. Okay? And the energy basically comes from when the nitrogen forms molecular nitrogen. I form that triple bond, which is very stable, and so I get a significant heat release. The other thing you find in some of these compounds can be highly loaded with hydrogen. So they're another mechanism of actually storing hydrogen. So if I wanted to add hydrogen because it has a low molecular weight to a propellant, then maybe I might be interested in adding some of these high nitrogen compounds. And so here are some of the characteristics of these compounds. And I didn't mention this before, but there's a rule of thumb. The higher the energy density of an energetic material, a strong correlation with is more sensitive, just as I told you about the CL20 and the. But what you see for these high nitrogen compounds is that doesn't exist. Okay, so there's no strong correlation with that. They also have very high burning rates at low pressure. Okay, so you can see here the pressure exponent's like 0.27, and the 6 centimeters per second at 100 atmospheres is actually pretty fast. You can detonate them despite there's no oxygen on them. They burn rapidly without a visible flame, and as I mentioned, they can have a very high hydrogen ratio as shown in this BTAZZ compound to the right here. Okay, so they're the type of compounds, and I want to go now and say a little bit about kinetics. You know, how do these molecules react? And if we wanted to build a reaction mechanism, how might we go about doing that? Okay, and a lot of this today starts with doing quantum chemical calculations. In the past, what I would do is I'd conduct experiments to try to measure the heats of formation of compounds using bomb calorimeters and things like that. And one still does that, but a lot of the calculations are done by first doing structural calculations, and basically evaluating and getting the heats of formation. And just to show you an example, if I know the heats of formation then, I can look at different types of reactions and start looking at bond strengths. And by looking at bond strengths, I can start estimating, crudely, how this molecule might start to react. Okay, so I recognize that the bond dissociation energy of, say, a molecule AB is just the difference in the heats of formation of that AB molecule and the heats of formation of the fragments that are formed, the heat of formation of A and the heat of formation of B. Okay, so as I said, if I tabulate all these heats of formation and I write down a reaction, I can start estimating bond energies. And just as rule of thumbs, and I'll show you more values here, if I look at the bond dissociation energy for a carbon-nitro group, and I compare it to a carbon-NO group, typically you'll find the CNO2 bond is stronger than the CNO bond. However, if I look at an NNO2 bond and I compare it to an NNO bond, they're about the same strength. If I look at the bond dissociation energy of a carbon NO2 group and I compare it now to that of the nitrite carbon ONO group, I'll find they're about the same. But if I look at the bond dissociation energy of the NO2 group and I compare it to the nitrite, I see that the NO2 bond is stronger. Okay, so if I do this, I can start creating tables of basically bond strengths and starting to estimate within the molecule where I'm going to get the initial fragmentation. When I break that bond, I might form a radical. Okay, then I might want to go back now and estimate the bond strengths in that radical structure. And if I do that, what you're going to find is those bond strengths differ a little bit from the neutral species. So as I note here, the energy required to break a bond in a radical species can differ from the bond dissociation energy. We must also consider the barrier to dissociation in addition to the bond dissociation energy. So the bond dissociation energy from removing the radical species from a radical adduct generally is less than the corresponding bond dissociation energy for the stable species. And I'll show you examples of that. Another reaction that you don't typically find too often in hydrocarbon oxidation or decomposition is what's referred to as concerted decomposition. So this is where I have a ring structure, and in one reaction, the entire ring structure comes apart. So on the left here, I show an example of triazine. Okay, so remember at the corner points here, these are just carbon atoms with 2 hydrogen. So instead of breaking one bond and then unraveling it, all 3 bonds can break at once to form 3 formaldehydes. And the same thing can happen in RDX. Remember, it had that ring structure. So you can again have a concerted decomposition and form 3 methylene nitramine molecules. Okay, this was actually studied doing molecular beam calculations, where I'd basically have an RDX molecule and I'd hit it with a molecular beam, put a lot of energy into it, and see how it fragmented. Something somewhat common to hydrocarbons is I can have a complex fission where I have a 5-centered group form and I eliminate HONO from the molecular structure. I'll show you some examples of that. The autocatalytic reactions are just basically radical attack reactions, very similar to a hydrocarbon where I might have an H radical come down and abstract an H atom, okay, to form H2. And the one that's somewhat different is water-assisted reactions. Often in hydrocarbon oxidation chemistry, particularly at low temperatures in the cool flame region, I basically have H atom transfer or an H atom shift, internal isomerization. Those activation energies can be still somewhat large. And to lower that activation energy, if I have a large amount of water in the vicinity of the molecule, it can actually lower its activation energy and make it proceed much quicker. So remember, in a condensed phase, I'm going to have a very dense mixture of molecules. And a lot of water from the early decomposition can be present with the primary reactant that's occurring. And so one actually sees potentially these water-assisted reactions occurring. So here's some examples of bond dissociation energies for various nitroso. Nitroso is when I have the remember, a nitro is when I have an NO2 group attached to the N or C. A nitroso is when I have basically the NO attached to the, I can have a nitrite, again, the ONO, and a nitrate, the ONO2 group. And so you can pick a few out here. So for example, if we're looking at something like methyl nitrate, so I take a look at this guy here, and I look at the bond energy to break the O-N bond. It's about 40 kcal, right? If let me see if I can find another example of that. Yeah, suppose I come down here. Here's the methyl nitrite again, nitrate. And now I'm breaking the CO bond. Look at the energy required to do that. So immediately it's telling me which of those two bonds is going to break, right? It's the ON bond versus the CO bond. And I can go through and look at other compounds. Say I have, remember I was talking about nitromethane, which has a CH3NO2 group, and I can compare that to, let's see, methyl nitrite. So here I'm looking at CH3NO2, and now I come over here to CH3ONO, and I'm comparing then breaking the CN bond versus the ON bond, and again, see again, it's the ON bond that's going to break in those. Okay, so knowing these bond energies, I can start formulating in my mind before I start building a detailed reaction mechanism and postulate reaction steps that are going to be occurring. Here's an energy diagram that illustrates simple fission versus this Hono elimination reaction. Okay, and so I show 4 examples here, and let's just concentrate on the one on the left. So as I said, this is an energy diagram in which if I go from left to right, I'm going from reactants to products, so it's a reaction coordinate. Okay, and in this particular case, I want to look at methyl nitrate decompose. Okay, and I know the weak bond because I just showed you. It's going to be this bond right here. Okay, and if I go back to that table, it had a activation energy, which is going to be related to the bond dissociation energy of about 40 kcal. So to do that, I'd have to basically climb this hill here. Okay, if I have this Hono elimination reaction in which I form a 5-membered ring internally here, what I'll find is forming the ring basically yields me like 33 kilocalories. And then when it actually breaks apart to release the Hono, I find the heat of reaction actually creates an overall negative exothermic reaction. So 2 things you observe. The first thing is it's going to take less energy for that Hono reaction to occur. And whereas the fission reaction is endothermic, quite a bit endothermic, the Hono reaction is exothermic. So it'll continue the reaction. The Hono reaction has a lower activation energy than the fission reaction. So again, if I plot an Arrhenius plot versus 1 over T, I'll look at a low activation energy process, and as I get to higher temperatures, I'll have a high activation energy process. So if I'm at real high temperatures, then I can start assuming, well, the thermal dissociation is going to take over something like Hono elimination. Okay, and so you can go all the way up here. If I look at this then and look at the notes below here, the top energy value represents the bond dissociation energy for NO2 bond fission. The middle energy value represents the barrier height for the 5-centered elimination of Hono, and the bottom energy represents the heat of dissociation for formation of Hono. Okay, and you can see that same process occurs for the other 3 examples that I show you here. Okay, this is an example of looking at, say, a simple abstraction reaction or an addition reaction. So I'm looking at methyl nitramine reacting with hydrogen atoms. And so if I look at the energy diagram again, going from reactants to products, if I look at the simple abstraction reaction, then this hydrogen atom is likely going to come over and abstract one of the H atoms. Okay, and I'll find then a barrier that looks like this, and I go to products that is slightly exothermic. Okay, if it's an addition reaction, I'm going to form an adduct. So because of the affinity, it's highly likely that the H atom is going to add to an oxygen atom. Okay, and so I'll get a structure that looks like this now with hydroxyl group. Okay, so now that adduct can come apart in a number of different ways. And I show some examples of how it potentially is predicted to come apart here on the right. Okay, so the one that requires the most energy is where I just fission off a H atom here. The most exothermic one, it still goes through a barrier here, but you can see is when I break the NN bond. Okay, so that's kind of interesting, right? Because if I go back and look at just the thermal dissociation of methyl nitramine, I can go back to this table back here. And if I look up methyl nitramine right here, right? And this N atom's attached to the N group there. So the energy required to break that NN bond is about 51 kcals, right? If I go through this sort of reaction with an H atom, adding to it, forming an adduct, basically the largest barrier occurs right here, which is about 10 kcal. So I'm comparing something of 10 kcal versus 50 kcals to proceed. Okay, so you can see how the H addition reaction, if H atoms are around, is going to be favorable. Okay, and here's an example of this water catalyzed reaction that I mentioned to you. Okay, so what I'm looking at here is basically just nitramine, NH2, NO2, and I'm going to look at how it can come up, how I can transfer, first, how I transfer this H atom over to the oxygen atom. So it's an internal isomerization of an H transfer. Okay, so proposed in the vicinity, I have a water molecule. And as I said, in condensed phase systems, or very high pressure systems, you have something referred to as a caged effect, which means that the density is so high, the reactants around it are hard to move away from that region, right? Because their collisions are so frequent. If I have an ideal gas, once a reaction occurs, you can assume the products are gone, right? But if I have this very dense system with all these molecules very tightly bound, that molecule as it comes apart is likely not going to move very far away, and it can still be active in the next reaction somehow. So here, in this particular case, I have a water very near this nitramine, and again you can see as it comes close, I'm going to basically transfer this hydrogen atom to this oxygen atom, and I'm going to transfer, as I form this ring, this sort of ring structure, this H atom is going to come over to the oxygen on the hydroxyl group then. And it's going to go away then with just water again, which came in, but I transferred the H atom across to the hydroxyl group through making use of the water molecule itself. Okay, suppose now I take this structure here, and there's another water molecule in the vicinity. Okay, so now this water molecule comes in, and I do the same sort of process. I form this ring structure. This H atom will transfer over to this oxygen atom. This H atom will basically form a bonding with this O atom, and I'll basically then break these bonds here to form water. This will come off to form water, and now I formed N2O. So the net effect of this reaction was to basically take the nitramine and form N2O and H2O, which is very difficult to see how it would happen, from a simple kinetic point of view directly. So as I mentioned here, in the first concerted mechanism, the H atom from the nitramine shifts to the water molecule, while the H atom on the water shifts to the oxygen of the nitramine, forming the ACI molecule. In the second step, the ACI molecule is converted to N2O in water by again having the H atom bonded to the nitrogen shifting to the water molecule, while the H atom on the water molecule is shifted to the OH group of the ACI molecule. Okay, so there's an example of some of the type of reactions that occur in these sort of molecular structures, some of which are very similar to hydrocarbon systems, but some you don't see often in hydrocarbon systems. So I put here, when people started to develop mechanisms and reaction mechanisms, they obviously started in the gas phase first, and more recently have been looking at the condensed phase. And historically, the procedure initially followed what happened in hydrocarbon oxidation chemistry. You'd start off studying very simple gas phase systems first, and this would be based on obtaining rate constant data, thermochemical data, and then performing simple experiments that might only involve an isothermal reaction, and monitoring as a function of time the species that evolve historically. Okay, and then building a kinetic model that can predict that. Okay, and then as I sort of, in quotes, validate that part of the mechanism, then I might say, well let's now add heat release to that system. So now I study it in an adiabatic system where now it's no longer isothermal. I include the temperature, and now that's going to affect the kinetic rates as a function during the reaction process. And I might now collect data under those conditions and compare the model. And then after I feel that's relatively validated, then I might try to add transport. So I'm starting to add now fluid mechanics to the chemistry. So there I might start looking at diffusion flames versus premixed flames, where the transport's been added. And that's what you see on the left here. So on the left, you can see gathering experimentally kinetic data. This again is rarely not done too much anymore because the theoretical modeling has sort of displaced doing isolated kinetic experiments for reaction rate constants. But as I start building mechanisms, if I want to do isothermal systems, people use shock tubes reactors, static reactors. They do that also in these energetic materials in the gas phase. And then they might go up to try to establish diffusion flames and premixed flames, and they do a validation with theory on the right-hand side. Ideas apply as much diagnostics as you can experimentally, and in the theory side, do as much detailed analysis, some sort of sensitivity analysis or whatever to make sure you understand what is the rate controlling reactions. And very similar to hydrocarbon chemistry, if I looked at a hydrocarbon burn, I know it goes through a sequential process. So I have a very large hydrocarbon, like, maybe octane. It starts breaking down very quickly the C4 species, C3 species, C2 species in a reaction path. And eventually those C2 species may go to C1, species such as methane and carbon monoxide. I eventually form hydrogen. Then at the very end of the reaction, that hydrogen and CO is converted to CO2 and water. Okay? And generally that's during that process of C2 to final CO2 and water is where the reaction is most exothermic. The beginning reaction is nearly isothermal. And so you can see here, if I was building a hydrocarbon mechanism, the first system I'd study is the one on the bottom here, hydrogen-oxygen, because it's a subset of all the other chemistries that I'm going to be building upon. Okay, it basically occurred at the end, but those type of reactions are occurring all throughout the mechanism. And then I might go up this chain here and start looking at carbon monoxide oxidation. And then once I feel I understand that, maybe go to formaldehyde oxidation. And then I can go in different ways, but I'm starting to add more complexity to the mechanism. So I'm approaching what would look like the early chemistry versus the late chemistry. Well, you can do the same thing in systems that are based on NO2 groups or NO3 groups. And I show an example here on the right then. So suppose I wanted to build a mechanism for these nitrate esters or nitramines. The nitrate esters are like the nitromethane, the methyl nitrate, and things like that. Well, what I know, again, the simplest chemistry is going to be the hydrogen, NO2, and N2O chemistry. So I'd study that first, and I'd move up this ladder on the right, depending on what was I thought of interest. But next I'd go to maybe carbon monoxide for the C side of the chain with those oxidizers, formaldehyde, methane, and then C2 species. And on the right side of the chain, to follow the nitrogen atom, I'd also want to look at, say, ammonia, hydrogen cyanide, etc. Okay, and then I'd have those individual submodels validated so that I have confidence as I add them. I'm only judging what is the new reactions that have been added to the mechanism that could be an error. Okay, so example here. These are flow reactor studies. This particular flow reactor at one time was Professor Dreyer's here at Princeton. And you can see the simple example here, first studying nitrous oxide decomposition on the left. This is a function of either position or time. If I know the velocity down this flow reactor in position, I can basically convert it to time. And so you can see, comparing a model to the experimental data, as the N2O is consumed, it forms molecular oxygen, some nitric oxide, and some NO2. And so the model was, developed to have good comparison there. And so having that part of the mechanism developed, the question is, well, suppose now I have the N2O react with methane. Okay, C1 species, and that's what you see on the right-hand side here. So as a function of time, you can see that the history and the intermediates become more complex. As the methane disappears, I'm forming C2H6, C2H4, C2H2. This is the same thing that would happen in hydrocarbon oxidation. And later on, after I form those, eventually I start forming the CO, and then at the very end of the reaction, the CO is converted to the CO2. Okay? And one of the reasons for that is what consumes, if you look, the methane hangs around all the way to the end, and the methane has to disappear before the CO is converted to CO2. What's the most important reaction that reacts with carbon monoxide? It's hydroxyl radicals. That's the main route for converting CO to CO2. So CO reacts with hydroxyl radicals to form CO2 plus H atoms. Very important in hydrocarbon and this chemistry as well. But what I'll find if I measure a rate constant, the reaction of OH reacting with methane is orders of magnitude faster. So if there's any methane around, the OH is going to react with the methane, and it's not going to react with the CO. So the only way that I can have the OH react with the CO is to get rid of the methane. So it's got to be consumed first. And then once it's consumed, the OH that starts forming reacts with the CO. Oh. Okay, and that's what you're seeing here. And it's the same sort of ideas that happen in hydrocarbon chemistry. Okay, so let's get a little bit closer to a nitro group molecule. So this is looking at basically some calculations, and the experiments can show the same thing, but this is a sort of an adiabatic calculation at constant pressure, okay, where I bring the nitromethane up above the autoignition temperature. And notice what you observe. The reaction has multiple stages. So initially, if I look at the temperature profile, the temperature doesn't vary too much. Then all of a sudden, I got this rapid rise in temperature. Then it halts, the temperature stays nearly constant. Then later on, I get a second stage reaction, which occurs. And the temperature finally goes to its adiabatic flame temperature. Okay, if I were to look at, how are we on time here? Probably getting pretty close, right? If I was to look at the species that are being formed as the nitromethane goes away during those reactions, you can see that as the nitromethane goes away, in this first stage reaction, I'm forming formaldehyde, forming some methane, forming some water, forming some NO, and some CO. Okay, and then sort of the reaction halts and becomes very slow. And this period in here, this is typically referred to as the first stage reaction. In flames, this is referred to as the dark zone because it's usually not luminous. And this is referred to as the second stage reaction out here. Okay, and what's basically controlling, again, this dark zone is both the methane that's formed here and the fact that the NO is very unreactive at these temperatures. So it's trying to be converted to hydrogen cyanide and N2O to make the reaction a little bit faster. And finally, I get to a slightly high enough temperature, and I get another explosive reaction. And the NO that's here can be converted to N2. Okay? This type of process shows up in flames as well, and you'll see it. Okay, so why don't we started a little bit late, but why don't we stop here for a break? So let's take the 15-minute break and come back about 5 after.